Continuing on with the evolution, form, and function of the Actinopterygii, the ray fin fishes, and how they move, so how they move through water. The physics of movement in fishes, snakes, mammals, all comes down to fundamentals of physics, basic physics. So when you learn about how fish move, you're going to be better prepared to learn how any other animal moves in general. But fish are kind of a special case because of the way they pass a wave down their body in order to move. Now, I want to point out that the fins also play a role, including an active role and a highly specialized role in some cases, like with flying fish, actually they function as airfoils. But let's look at just the basic idea here, which is that what's going to happen here with fish is the fish is going to pass a wave down its body. Now, I'm going to look at two different analogous systems here, which are not great analogies, but I think we can take away some valuable aspects of that by looking at them. First I wanted to look at is an example of, I have to find it again here, the Archimedes screw. This is, again, not a great example, not a great analogy, because fish don't move anything, do not pass a wave down their body, anything like an Archimedes screw. But what you do see with Archimedes screw, the pump, which is a way of moving water, an efficient way of moving water, is you see a wave pass down a body which does not change in length. You have a fixed length, so if a fish has a fixed length, you're going to pass a wave down and exert a net force in one direction, either forward or backward. You're going to go forward, you need to exert a net force in the water going backwards. That's one analogy. Here's another analogy, which is breakdancing. So if you watch this person here, it's this kind of it's a simulated wave. You're not actually propelling yourself in one way or the other. This is art, basically, performance art. But the way that breakdancing works there, the way that the arm wave is similar to the way that a fish passes a wave down its body. So hopefully we'll see here when the whole thing goes. So there's the wave passing through the body, goes out. Well, what's noticed there, what he did there is he started the wave out at the tip of his hand. When you watch the eel here, the wave starts at the head, and the head moves up and down. So if you're an eel, the problem with one of the probably many problems with being an eel is that your head moves around as you swim. So the wave is generated along the entire body. I think the Archimedes screw is somewhat similar in that way. And it starts with the head. So if the eel was a breakdancer, it'd be doing something similar with the arm wave there. And what you notice here is, what you see here is a coordinated contraction and relaxation pattern, so that first of all, you are contorted into there's a series of waves here, but there is a bend which is going to effectively pass down the body, just like a bend was effectively passed down the Archimedes screw or across the breakdancer's arms. You watch it, it's sort of mesmerizing. It's almost like an optical illusion. The wave is passed down, except that it's not. There really is a wave passed down the body. Why is this important? Here's why it's important. We look at a diagram. When you, I'm going to look straight at the camera here. If I do this, imagine you're in water. It's easier to imagine water because it pushes back on you more than air does. And you know how hard it is to move through water if you're walking through water. It pushes back on you pretty hard. So a fish that pushes on the water gets a pretty strong push backwards because it has to push harder to do that. And if I simply take my hand and go back and forth, and my hand was rigid, what am I accomplishing in the water? Nothing. And if these were flippers, and all I was doing was going up and down with my feet, what is that accomplishing? It's not accomplishing anything at all. You're pushing water up, you're pushing water down, and so you have a force going up and a force going down. Where's the force going forward? Where does that come from? It's not there at all. And imagine instead it's a flipper or a fin or a fin-shaped thing. Now imagine it going up and down. Again, if it's rigid, you're pushing up on the water, pushing down on the water, you're getting a force up, you're getting a force down. Where's the force going in one particular direction, the forward or backward? There is none. But that's not what flippers do. Flippers bend. They're flexible. So what you don't see when you're using flippers, if you use them to swim, to speed yourself up. Otherwise, you just got to use your feet to do it. What's happening here is there's a wave generated that's passed down the length of this. So I pull up, I'm going up, and the water pushes back on me. See the bend? Likewise, on the down stroke, a bend is generated and it follows, right? So in the process of following, there's a moment where there's a bend. And if you were to trace the net path of that bend, you get a little push back against the water, which results in an equal and opposite push forward. You push back against the water, you are pushed forward. If I push against this wall, I go that way. It's basically pretty simple. What's not simple is, of course, having the musculature and to actually make the bend happen. So if you watch a swimmer here, I've slowed this down. So that now I want to point out something is that the arm part of swimming is not something that fish do. It's not something. That's not how penguins move through the water at all. They actually fly through the water. So just ignore the arm part. Look at the foot part, the leg part. And of course, this person's wearing fins. What's happening here is a wave is being passed down the body so that there's now all kind of motion is happening here. You have pushes going up against the water, does nothing for you. Pushes going down, just counters that last force. Okay, there shouldn't be any side to side if you're a good swimmer. So what does that leave? If the legs are contributing anything, it means they exerted a neck force going back, right? Which means that there had to be a push back against the water. And since the leg didn't get longer, right? So then we know it must have happened. So in other words, a net wave must have been passed back against the water, even though maybe you don't really see that, or maybe you do see it. This is sort of doing some other thing here too, but from the tip of the fin, the base of the leg here, the wave is being passed a net back such that there is a net force exerted against the water back. Any other forces exerted here are wasted energy, but they are necessary in order to generate the wave. The case of the eel, the process of generating this bend and doing it in a way that it appears to pass down the body, and it does pass down the body, requires a coordinated contraction and relaxation process. So that, again, we have the side-to-side forces cancel out, and what's left is a net force going back. How about shorter fish that don't move like eels, like normal fish, like a trout? The head does not go back and forth like that. Instead, you have the back half of the body generating that wave that effectively moves back. And by the way, there are more complicated physics involved in this. If you ever read, there's a nice lecture online about how the physics, if this was an advanced ichthyology class, there's actually more to it than this. But this is true. What I'm telling you here is this is factual. There's just more to it than this. So a typical fish, and we'll look at examples of this, are going to pass a body, but they're not going to have as much, as long of a distance for that wave to go. So they're going to have to keep generating it over and over again. But what it looks like to you when you see them swimming is it just looks like it's going back and forth. But of course, that's not what they're doing. Put your hand in water and go back and forth. Hold your hand rigidly. You can see it doesn't exert any force forward or backwards. How about something like a fish, like these little box fish, and just the end of the tail? Yep, still produces a. It's like the end of a, it's like the end of a flipper. It does that. So you get a net force going back. So let's take a look at some videos here that show this. This is a nice video of fluid dynamics. So that's another thing that's happening here is fluid dynamics, which are related and are far more complex because there's friction forces pulling on you as well as you move through the water. And so there are forces that tend to counter that as well, all beyond the scope of this class. There are physical laws. But what you see here, what's really nice with this illustration, is you can see the net force going back. Obviously, there's also forces side to side. See the angle of them? So there's a push that way and a push that way. So if you could put your hands on either side of the fish, you would feel a little, maybe you might feel a little bit of the wave. In fact, that's what the other fish in the environment can feel when a fish swims by, is those vibrations that are created by that side to side movement. And that movement really doesn't, it's, you have to make that side to side movement to generate the backwards movement, but it's, somewhat like friction. Here, look at this is the anguilliform. Look at the head moving though. So anguilliform locomotion, the head generates the wave, just like the breakdancer's tip of his finger appeared to generate the wave. Look at the net push back on the water, resulting in a force, the object going forward. Where locomotion gets very complex is in this case, the fluid dynamics, in the case of bird wings with the aerodynamics, in the physics of waves and vortices. But what's shown here is over which, the length of the body the wave is passed. So how much of the body is contributing to this? It varies among fishes. Let's take a look at some of these. So here's a really nice illustration here of swimming. I've slowed it down. And so this is in a moving water column. It's using its pectoral fins, like we use our pectoral fins when we swim, and the tail. If you watch the tail, it's going to bend right there. So what was happening there, the water is continuously moving, even though you can't see it. To stay in one position, it had to do something, right? So you can see the pectoral fins contribute a little bit to it. But right there, look at that. There's your bend right there. If you were to follow that, you would see there is a net force going back. And then look, it doesn't always do that. So I find fascinating about this video is it's able to sort of move its pectoral fins, which I assume is kind of like human swimming. You're just pushing back on the water. On the other hand, I'm actually not sure. I know probably some fish can actually use those pectoral fins to generate a wave in the same way the tail generates a wave. What's important here is that the pectoral fins also contribute as well. But look at the wave passed down the body, but only the second half of the body. The first half of the body is rigid. The first part of the body has other things to do besides generate the wave. Here's a swimming only with pectoral fins, so they can do it. Although actually, I think there is a slight. It seemed to me there was a slight bit of movement there that might have been contributing, but not much. How about tuna? Tuna, of course, are some of the fastest swimmers, and yet most of their body does not generate a wave. The wave is generated back here in the tail. And as you probably know, the tail of a tuna is actually a prize thing if you harvest tuna for food. there's a lot of muscle tissue in there. It's got to have a lot of muscle tissue because of what it does. So there it is. Most of the tuna is rigid. And the rest of it is generating the wave. The tail is generating the wave. What else about the tail do you see there? You see an aerodynamic shape. You see aerodynamics, not aerodynamics, these are fluid dynamics, but you see fluid dynamics here. These fins here, the dorsal fin, which control pitch and roll and yaw and all the different movements, and also tend to reduce the friction and provide just a more aerodynamic, a more fluid dynamic, that's the word for it, but a smoother passage through the water. You're going to generate little eddies and when you swim. And you want to minimize those because those pull back on you. So much of the shape of the fins has to do with that. Extremely fast. And you can't really even see sort of the breakdancing like wave passing down that tail, but it's there. Other fish actually use their pectoral fins, like rays, as wings in the same way that birds use theirs as airfoil, something we're going to learn about in lab. You won't have a wave being passed down the body from head to tail. Instead, the wave is generated along the pectoral fin. What good does that do you? Well, what it's doing here is it's flying underwater. So those are actual airfoils. Airfoils, these are not limbs moving like the swimmer's limbs were moving. These are airfoils. That is true flying. Completely different story. So it's generating lift and propulsion by changing the angle of attack of the wing and yeah. So fish differ in how much of the body is contributing to this. So here we have, there's different terms for them. Anguilliform, the whole head movement is a strong head movement. In case of salmonids, there's also strong head movement called subcaringiform. The caringiform head movement is not much head movement. You can't even see it. That's a good thing, is to not have to move your head as much. And then the tuniform, buniform, is the tuna form which the head does not move hardly at all. Imagine trying to focus on prey or predators when your head's moving side to side. The tuna have been able, they're even faster than eels, and they don't move their head. So there's a lot of variation in the extent of the bend of the curvature that you actually see. Extent of the head undulation. And think about this, the nature of this and what this means. So, this is just a much different way of moving, and this is not going to be this eel's not going to sneak up on anything. This eel's not going to race up and grab something. This eel, the way it feeds, it's going to have to feed in different ways. And honestly, I don't know what it eats. But it's not going to sneak up on anything. And it's not going to get away from anything fast. Yeah. Eels are pretty funny. Here's a nice diagram here showing the different types of forms. So what you have here on a scale on the X and Y here is on the X axis, you have the extent of head movement. Does it undulate back and forth versus oscillation, which I guess is not as much head movement. So off to the right here, we have not as much head movement. To the left, we have great head movement, starts at the head and passes down. On the y-axis, what do we have here is how much of the body is used for the generating that wave. For example, trunk, these fish here generate it in the trunk and in the tail caudal region, whereas those here at the top, the wave is generated in the very tip. Well, actually, it's not perfectly lined up here in an XY graph, but this is the way they've organized it. So, for example, the ameiform. Oh, I meant to. Do we have an ameiform? This is the other way. I have to bring up this video here. This is a bowfin once it comes up here. There's we'll see a bowfin, the way they move and use their fins. They do something a little extra, which is they pass that wave down the dorsal fin, as you can see. They also move their tail in a way that generates a bend passing down the length of the body as well. And there's different examples here we're going to look at. Rajiform, which is using the pectoral fins to generate actually lift the same way the bird does. The labriform, we'll look at examples of that. Let's just take a look at these examples here. This is probably the most extreme example of caudal, where the wave is used. So how does a boxfish move? That's a good question. So one thing, it's hard to see, but their little pectoral fins are moving very, very rapidly. There's that. So I believe that's just simply moving, pushing against the water. And there's the little tiny short tail. Which is, you can barely see, but it's there, tiny little tail. And there's enough, apparently there's enough length in that little tail tip to create a propulsive force. How about a wrasse? Something like a tautog. This is not a tautog, but it's in the wrasse. Notice how much of the front of the body is fixed, and where the wave is generated comes from, the motion comes from the pectoral fins and then the caudal region. But it's all fairly similar. They're all in an aquatic environment, and what they're pushing against pushes back hard. And it's hard to push against water. They do not have gravitational forces as a significant part of their movement, really. And another thing about them is that the forces are equal on all sides. And so they have to deal with compression, which does place limitations on other aspects of their life. But basically fish, they need to be shaped, either if they're not shaped like a, think about the submarine shaped fish, something like a trout. And then of course you have the flattened shape is dorsal laterally flattened. And that is, very, very different, but you can see though, you're either, you can move in a stream-like way, reducing friction by being sort of smooth and torpedo shaped, or you can be very flat and thin, so that you're not pushing up against a lot of water as you move. All different ways of doing the same thing, which is reducing friction. But we see the importance of the fin movements as well. And I'm just this is just glossing over a lot of highly complex movements. I didn't even talk about the pelvic fins or the anal fins or the tail fin itself and all the dynamics of that as well. In the next part, we'll look at reproduction by the ray fin fishes.